Okay, so we're going to be starting the last chapter, well, the last chapter for us from further mechanics, and this is called elastic strings and springs. And it really is going to just be adding into like different mechanic situations, things that instead of just being attached to a string, they normally say that that string is inextensible, it is now just going to mean that they can actually stretch. So if you think about your lanyards, basically your lanyards are inextensible. They're not really going to be stretchy at all. So as we go to something that is going to be stretchy, there are going to be different kinds of things that can happen. Some of those things that might happen might be that something is hanging on a piece of elastic and it might get pulled down and then it might get released and then that particle is going to accelerate and it's going to move and different things like that, okay? Other things will get more complicated. There might be a particle that is attached to a string or a spring and then is placed on a slope where the string is attached to the top end of the slope and it may be pulled down the slope, and we just are going to decide how that thing might move. Is it going to move up the slope, or is there going to be so much friction that it's not going to move? So we haven't looked at lots of these forces for quite a long time because we were doing collisions beforehand. So if you need a reminder of any of these things, like just ask for them, because this is obviously quite sophisticated mechanics that we're doing here. Okay, we're going to just dive straight in with how some of these things work here. So Hooke's law says that when an elastic string or spring is stretched, the tension T produced is proportional to the extension or compression. Why have I said or compression? Because if you squeeze it in, if it's a spring, you can squeeze it in. If the question is obviously a string, you can't compress a string because it will just go loose and the tension will just become zero very, very quickly. So the tension is equal to lambda over Lx. So you can see here that it is proportional to the amount that it has been extended. However, we probably, and this is just really semantic, we probably usually think of it as lambda x over L. I don't know why, but that's probably the more familiar way that I will be saying it, as lambda x over L. But I wanted it written in this way so that you could see that the tension is proportional to how much it has been stretched, okay? Lambda is known as the modulus of elasticity, and we'll talk about that in just a second. And L is the natural, meaning the unstretched length of either the string or the spring when it's just kind of lying on the table with nothing interacting with it. What else was I needing to say here? When I do my L's, you'll notice I do my L's kind of like a curly shaped L, and I really want you to be doing that. If you say that it's over L like this, you may well think that it's over 1, and that's kind of confusing. So a note about the modulus of elasticity. In A-level maths, the modulus of elasticity refers to this lambda in the equation that we have there. And lambda can be understood as the force needed to double the length of a string or spring. So lambda's actual units are in newtons, okay? This is just the definition of how they came up with what this what lambda was going to be, what the modulus of elasticity is. So it's the amount of force required to double the length of the string or spring. You never really have to use this in any of the calculations, but it's just interesting to know how you can interpret what that is, and to remember that the units of the modulus of elasticity are newtons. Last of all, for those of you who do physics, lambda and the modulus of elasticity should not be confused with Young's modulus, which is a constant that we do not use in A-level maths, but it does come across, you will come across it in physics. And in physics, they sometimes call it the elastic modulus, but they are slightly different things, and I haven't done physics since I was your age, so I actually can't remember like what the same and different things are. So you'll probably be in a better position after we've studied this to know what's the difference between them, okay? So Hooke's law, like, what is it and when does it apply? So many springs, strings, wires, and solids obey Hooke's law in a limited range. Hooke's law only ever applies up to a maximum force known as the elastic limit, which varies for each spring or string. Under a very large force, springs deform and break. You ever had a slinky when you were younger and like you stretched the slinky so much that it never went back to like its original state? So after that original state there, when it's gone all like the string or when the spring has gone all stretched out, it is no longer elastic anymore. It's not going to shrink back to what it originally was. And after that point, Hooke's law will not apply because that spring has deformed there. You can also kind of think of that with, I don't know, it's not really so true because elastic bands always do tend to come back. But sometimes if you stretch like a piece of rubber so much and then it doesn't return to its original form. That's where it's gone beyond that elastic limit. So if a string or spring obeys Hooke's law, it is called elastic. So you just look out for that word elastic being used, or extensible in the questions. An elastic spring can also be compressed. Sorry, an elastic spring. Did I say spring or string? I hate that those words are like basically the same. So the spring can also be compressed, which produces thrust instead of tension, meaning that it's got like a pushing force away. However, elastic strings obviously don't resist compression. So you can think about your lanyards as you kind of pushed two ends of a string together, the string just completely loses any of its tension. All strings and springs, in A-level maths anyway, are light, so they don't extend under their own weight. But that's probably a useful thing. You know, when they say, what modelling assumptions have we made? If they have said in the question that the spring is light, then actually you could say, in reality, the spring is going to have a mass, which means that it would stretch under its own weight, okay? It would also mean that the tension wasn't necessarily equal throughout, because the bottom of the string would be having to carry the weight of the top of the string, and the top of the string wouldn't have to be carrying anything at all. Okay, so just a bit of a graph that kind of shows some of the things we were talking about at the top here. The force and the extension, so the tension increases in the string up until a certain point where the elastic limit happens, and then the force actually kind of levels off, but it actually extends quite a bit more. So with the idea of a slinky, it like stretches to a certain amount and the force increases proportionally. You keep stretching it and it's going to actually get really stretched out, and the force isn't going to increase very much. And so this point here is the elastic limit, where it's no longer got this directly proportional relationship that we have. So let's just quickly see what I've written here. Graph showing the extension of a spring as the weight is hung from it, and hence the tension in the spring increases. The variables are in direct proportion up till this point, obeying Hooke's law, which goes up to the elastic limit, beyond which the law doesn't hold. So really, that's the theory, okay? That is the theory, and we're just going to start applying this into various contexts. I'm not going to be able to go through every kind of context that they might be able to suggest this to you, and this is kind of this is what makes this module become like a further maths module, because they're always going to be able to come up with a scenario that is something we haven't quite seen before. So we'll do as many as we can in class, we'll do as many as we can in exercises, and then when we're preparing for the exam, we'll look at as many exam questions as possible, so you're in a really strong position for this. So it's going to start off nice and easy here. An elastic string of natural length 2 meters and modulus of elasticity 29.4 newtons has one end fixed. A particle of mass 4 kilograms is attached to the other end and hangs at rest. Find the extension of the string. Okay, so what this is going to look like as a diagram is it's been attached to one point, so seems like it's talking about it's been attached to like a ceiling of some kind of thing, and this string is hanging down and there is a particle that is attached to the end of it, and it says that the particle is hanging at rest. So I guess there's just a few things that I want to be able to add to this diagram. It's not going to be a particularly exciting diagram, but tell me a couple of things I could add to this diagram. Pardon? So I could add the natural length to it, but it's not, this length of the string at the moment is not going to be that because it's already stretched a bit. So I'm probably just going to write somewhere on the side of the page that the natural length is equal to 2. The particle mass is 4 kilograms. So where am I going to put that? I'm going to have it coming out of here, and I'm going to write 4G. I know this is basic, but we haven't done it for a while, so we just want to make sure we all remember those things we need to do. So what other forces need to be on this diagram? Shahan? Yeah, there's going to be the tension in the string, which is acting upwards like this, okay? So if this were nothing to do with the elastics, if this was something that we were just doing in mechanics last year, what would the value of the tension be? 4G. Yeah, the tension is just going to be equal to 4G because this is at rest. It's not moving, okay? So it is in equilibrium. So the tension is equal to 4G. What we did there is we resolved in the up and down direction to just say that they're equal to each other. But now the question says, find the extension in the string. So how much has it actually stretched for that to be right? So we know that the tension is equal to 4G, but we also know that tension equals lambda x over L. So we can just substitute everything into that formula, and that will be able to tell us what the extension is. So T is 4G, lambda is 29.4, x is the extension, and the natural length is 2. Does anybody recognize what they think 29.4 is in terms of G? It's 3G, because it's a weird number, so that's actually 3G over 2, so it becomes 8G over 3G, which is just 8 over 3. Okay, you could just put it in your calculator with G, but 29.4 to me made me go, huh, that's a weird number, I wonder why they've done it. It's a multiple of G, okay? So x is equal to 8 over 3. However, this is mechanics, so 8 over 3, 3 significant figures? Good, 2.67 meters. So the extension in the string is 2.67 meters. It's actually extended quite a lot, yeah? It's extended an awful lot there. And that kind of makes sense because, yeah. So it's stretched quite a lot there. And what are we going to say? That's what I wanted to say, actually. The modulus of elasticity is 3G. And do you remember what the definition of the modulus of elasticity was? The force needed to double it. So the force here is 4G, which is more than 3G. So hence it has more than doubled in length. Okay, you don't ever really need to think in that kind of logical way, but it's kind of nice to return to that definition and think why that's true. They might ask you different questions. They might not say, find the extension in the string. They might ask you, how far is the box now below the ceiling? And you might have to add on the original 2 meters as well to get 4.67 meters, okay? So just make sure you read what the question carefully says. In this case, it just asked for the extension. It didn't ask for what the total length of the string was, okay? So we're going to just do another one of these. But we now don't get a diagram, so just try and, we're going to read it, and I'm going to give you a couple of seconds to think about what it might look like. This time it's a spring. An elastic spring of natural length 1.5 meters has one end attached to a fixed point. A horizontal force of magnitude 6 newtons is applied to the other end and compresses the spring to a length of 1 meter. Find the modulus of elasticity of the spring. So just have a quick think about what this diagram might look like. You can draw it if you want to. So is it going up or down or left and right? Left and right. So we're going to have one bit where there's the spring is attached. When I do springs, you can just do straight lines, but I always do like spring shapes just because it reminds me that it's a spring. You don't have to. So we've got a spring and it's been compressed with a force of 6 newtons. So there's a force pushing it inwards with 6 newtons like this. What does that then mean that the spring is doing? The same and back. And what type of force is it? Thrust. Good. So the spring is pushing back with a thrust that is also going to be 6 newtons because it doesn't seem like there's anything that's saying anything is moving here. Okay. I'll probably just write down a couple of things. I'll say that the natural length is 1.5. Anything else that it's told me about in the question? So it's gone to 1 meter, which means, good, the compression is 0.5, but yeah, it's the same thing, it's x. X is going to be the compression or the extension in this case that we've got. Very clearly, from resolving left and right, we can see that the tension is equal to 6, and we know that tension equals lambda x over L. So tension equals lambda x over L. And then when we solve that equation, what do we get there? Is it lambda equals 18? So it's a little bit different what the modulus of elasticity means here, because we said it was how much it was to double the length of the string. 18 is this is compressing it by a third of how much it originally was, because it's doing a third of the modulus of the elasticity, which implies that if you did all of the modulus of elasticity, it would like squash the whole thing down. So it's just a little bit different with compression, which is why it's usually better just to use the formula rather than to try and think of it. That's 18 newtons. Yeah, the units for the modulus of elasticity is 18 newtons. Obviously, these are going to become a little bit more complicated in a bit. So I've got here a few sentences that I want you to avoid using the formula, particularly for the ones that are extensions. I just want you to try and think from the definition of the modulus of elasticity what the tensions and things might be. So for example, in this first one, the string has natural length L and modulus of elasticity 1, 2, 3 newtons. It is stretched to a length of 2L. What is the tension in the string? So it has doubled in length. So the modulus of elasticity is 123. So the tension in the string would be 123, okay? For this particular first one, the tension would be 123 because it's doubled in length. If you can't see that, if you can't see that logic that goes behind it, you could say that the tension is equal to lambda. The extension is gone from L to 2L is L, and the original length is L. So that's lambda x over L. Oh, sorry, the original L is L. And so you get that the tension is 123. So if you prefer using the formula, you can use the formula, but most of these can just be done with common sense. Read them all really carefully and have a go of what you think that they might be. Okay?
Do you think a good way of thinking about it would be like, if you apply the lambda, it adds like an extra length or takes away an extra
Yes,
length?
I think that's a really good way of thinking about it. Yeah, if you apply that lambda force, it either adds that length or takes it away. Obviously, with a spring, you'd have to be, there's a limit to that, isn't there? Because you can't compress it any further. No. We will never do questions that go outside the elastic limit, ever, okay? Hooke's law doesn't apply, and it just becomes engineering level maths. Okay, maybe just like 20, 30 seconds. Don't worry if you haven't finished them. They're just little thinking puzzles rather than... So let's have a look at the second one then. So we have natural length L, modulus of elasticity 123, and it's stretched to a length 3L. So what tension would be required to make it go to triple its original length? Not going to be times by 1.5.
123L.
It's going to be 123 and then another 123 to stretch it. So it's going to be 246, okay? So it's actually kind of the way that Sam said it, of each modulus of elasticity adds on an extra natural length rather than it being like it's additive rather than proportionally like multiplied. Again, you could also just check it by doing that it's lambda, the extension is 2L over the natural length, so you get 123 times 2 as well. It's quite nice just to see it with the formula. So this one is slightly different in its wording. It says it is extended by a distance of 2L. So it's the same as this one because it's actually ending up at the overall distance is 3L. So you've got to be really careful in these questions because sometimes they might tell you what the string length is, sometimes they might tell you what the extension is, and you've got to be careful about identifying that. Okay, this one is what's going to be the modulus of elasticity and y for this one? It's 99. Yeah, why is it 99? It's doubled in length. Okay, it's gone from 3 meters to 6 meters. So that is the definition of the modulus of elasticity. It's the force required to double the length. Again, x is the extension, not the new length. No, not the total length. So if we were going to solve this one here, we could say that the force equals lambda. The extension is 3, and the original length is 3. So you just get lambda is equal to 99. This one's a bit trickier. Anyone got any what they think it is just from like the common sense? Yeah, from like the kind of common sense of this, the force, the compressive force is going to be 10 newtons because if it was to compress to its 0 length, that would be what the modulus of elasticity is, but it's only being compressed from L to 3/4 L, so the compression is 1/4 L. I find that one just a bit harder because yeah, so I would say that the tension is equal to lambda. The extension is, the compression is 1/4 L, and the original length was L. So you've got 40 times 1/4, which is just obviously going to be 10. And what about the last one? What do we think the value of x is going to be in this?
3/4 L.
It's a trick question. It's a trick question, the last one, because a string is compressed. It's just a lesson in reading things really carefully. So this one is a trick question. Pardon? Springs can just be, yeah, I mean... So yeah, but what's its compression? Like nothing, it's still the same length. It's just all squiggles and around. I put that in to just be annoying, really. I mean, you're never going to have a question, I hope, that like you spend the whole thing thinking that it can be compressed, and actually the mark scheme just says like for 7 marks, it's a string, it can't be compressed. What are you doing? Okay. So I'll just finish that bit up here.